Welcome to this explainer on the kth largest integer problem. Now, we've all seen this classic coding challenge, right? But what's really fascinating here is how it literally separates the junior coders from the seniors. Because, it's not just about getting the right answer. Anybody can do that. It's really about testing how well you truly understand algorithmic trade-offs. So let's just dive right into it.
I want you to think about it like this for a second. Does it actually make sense to rank every single player in a massive global tournament just to find out who gets the bronze medal? Well, of course not. That would be a complete waste of time and energy. And in computer science, doing that is a massive waste of processing power.
So here's the exact problem we're tackling today. We need to return the kth largest integer in an array that contains no duplicates. Say we've got an array of 6 numbers, 5, 2, 4, 3, 1, and 6. And for this example, let's just set our k to 3. So out of this entire list, we just want to pinpoint the third largest integer. Simple enough, right?
Now, the absolute most obvious, kind of naive solution, the brute force approach, is to just sort the entire array in reverse order. Once you've got it lined up from biggest to smallest, you simply grab the number sitting at the k-1 index. But, well, here's the catch. Sorting the whole array costs a pretty heavy O of n log n in time complexity.
And honestly, this brilliantly illustrates exactly why full sorting is kind of the villain of inefficiency here. We've got our O of n log n brute force method, sure, but since we literally only need that single kth largest integer, sorting everything is frankly overkill. So this completely sets up our journey to find more optimized data structures. We want to find our target number way faster, hopefully dropping that time down to O of n log k, or hey, maybe even better.
All right, let's bring in our first algorithmic hero. Approach 1, the Min Heap.
The really clever intuition here is this. Instead of sorting the whole shebang, what if we just keep track of only the top k largest integers as we scan through the list? Let's walk through initializing our Min Heap just to see how this actually works in practice. We're going to build this up pretty rapidly. First, we look at the very first element in our array, which is a 5. We just take that number and push it right into our Min Heap data structure.
Next up, we move to the second integer in our array, a 2. We quickly add this 2 to our heap as well. You can kind of think of our heap as the top k medalist spots on a podium, right? And right now, we're just starting to fill those empty spots up. Then we go ahead and push the third integer, the number 4. Now, notice what happens here. Our k is 3, and our heap now contains exactly 3 integers, 2, 4, and 5. The heap is completely full. So from this point on, once the heap hits that k limit, we can't just blindly add numbers anymore. We actually have to start making decisions about who gets to stay and who gets kicked off the podium.
And this is absolutely the crucial turning point. The next integer in our array is 3. We compare it to the smallest number currently sitting in our heap, which is always right there at the very top, in this case, the number 2. Now, since our incoming 3 is greater than the heap's minimum of 2, well, 3 is clearly a much better candidate for our top k. So we kick out the 2, just pop it right out of the heap, and push our new contender, the 3, right on in.
Okay, let's slow down for a second here, because I really want us to grasp why this next step is just so powerful. The next integer in line is 1. We check our heap's current minimum, which is now 3. Because 1 is strictly smaller than 3, we just completely reject it. We know for an absolute fact that it cannot possibly be in the top 3 largest integers of the entire array. So we literally just skip it and move on. No wasted processing whatsoever.
Finally, we arrive at the very last integer in our array, which is a 6. We run our standard check. Is 6 larger than our heap's current minimum of 3? Yes, for sure. So we can confidently pop that 3 right out of the heap and push the 6 in.
Now what's super interesting here is the final state of our heap. We've processed the entire array, right? Those k integers currently sitting in our heap represent the actual verified top k largest integers overall. And because it's a min heap, the smallest of those top-tier values is just sitting right there at the top. That number 4 is our grand prize. It's the exact kth largest integer we've been searching for all along.
Let's quickly summarize the trade-offs of this approach. Notice how our time complexity just drops beautifully to O of n log k. That's because for each of our n integers, we're performing at most one push and pop operation on a heap that never ever grows larger than size k. And each of those heap operations just takes O of log k time. Now, it does cost us O of k extra memory space to actually store that heap, but honestly, it's a really fantastic trade-off. All right, let's move on to approach 2 and see how we can build out our optimization toolkit even further. Enter Quickselect.
So Quickselect asks a pretty fascinating question. Can we somehow just drop the specific target number into its exact final sorted slot without maintaining a secondary tracking list or heap at all? Well, it relies on a super clever mathematical trick. Usually, this algorithm is used to find the kth smallest element, but we want the largest, right? Well, finding the kth largest integer is mathematically identical to targeting the n-k smallest index. Think about it. For our array of size 6, finding the third largest is perfectly equivalent to finding the index 6 minus 3, which is just the third smallest.
Now, if you're already familiar with the famous quicksort algorithm, you'll definitely want to contrast it directly with Quickselect to really appreciate the optimization happening here. In quicksort, we pick a pivot, partition the array, and then recursively process both the left and right parts to sort every single thing. But Quickselect, it saves an immense amount of time by only recursing on the exact half of the partition where our target actually lives.
So how do we decide which half to search? Well, we pick a random pivot and partition our array. If our randomly chosen pivot lands at an index before our target index of n-k, boom, we instantly know our target must be somewhere over to the right. So we completely ignore the left side and perform Quickselect purely on the right part.
Conversely, if the pivot overshoots and lands after our target index, we know for sure the number we want is smaller than our pivot, so we can safely discard the entire right side of the array and exclusively search the left side. It's so efficient.
And guys, here is the absolute magic moment. If our pivot happens to land exactly on that index of n-k, we have struck gold. The pivot itself is perfectly positioned in its final sorted spot, which means it's our target number. We've found our kth largest integer, we can immediately return it and just stop searching entirely.
Let's take a look at the final metrics here. Quickselect achieves a truly fantastic O of n average time complexity, mostly because we're essentially cutting our search space in half with every single recursive call. But I definitely have to warn you about the dangerous O of n squared worst-case risk. If your random pivot selection is just extremely unlucky and consistently gives you these terribly unbalanced partitions, your performance is going to tank. As for space complexity, it's super lightweight, averaging just O of log n for the call stack.
Which brings us to the ultimate question to wrap up this explainer. Which trade-off are you actually willing to make? Do you choose the Min Heap for its guaranteed time performance, knowing full well it's going to cost you that extra O of k space? Or do you gamble on Quickselect? You get that phenomenal average linear speed and near zero extra space, but you have to accept that slight worst-case risk. Honestly, the right answer depends entirely on the specific constraints of the system you're building. So, what would you choose for your next big project? Think about that and happy learning.